Thank you for having me here. Right, so planned is 2 lectures, and today I want to talk about the first part, existential theory of the reals as a complexity class, and tomorrow I'll hopefully talk about applications to game theory. So this will be in 2 different parts. So I was thinking about how to motivate the problem or the area. Start with something that we know, so we can look at the traveling salesman problem. Let me just remind you so what that is. So we are given distances between n cities and the budget. The question is there a TSP tour visiting all the cities in such a way that the total distance traveled is less than or equal to the budget? So is there a permutation pi on the set of cities, and let me number them from 1 to n-1, such that the distance, so we sum from 0 to n-1, we let pi I be the ith city visited along the tour, so we take the distance d pi I to the city d pi, where we take I plus 1, and then we do mod n to keep it in the range. We want to see if this is less than or equal to the budget. So well-known NP-complete problem, so which you have probably all seen or taught many times. So what I would like to talk about first is the Euclidean traveling salesman problem. So now we are no longer given distances, but we're just given points in Euclidean space describing the location of the cities, and then the distances are going to be the Euclidean distances. Right, so instead of having these distances, we're going to have cities x0 up to xn-1. Let's say they live in d-dimensional space for some d. And we still have the budget. We still want to ask about a permutation meeting the budget, but now the distances are the Euclidean distance. So where dij, that is then just the following thing here, k from 1 to d, xik minus yik squared. So what do we know about this problem? We know this problem is NP-hard, so just as the normal TSP problem.
How do you get real numbers?
Yeah, so how do you get real numbers? So let's assume it's not real numbers, but let's assume that we have, you can assume having rationals for now, and maybe I'll say something about, I'll probably not say something about real numbers in relation to TSP, but we'll see. Right, so this here is NP-hard. I'll not argue this, or you can look it up. Probably you need a different proof than the one you're used to. So what is open here is NP membership. So which is usually the easy case in an NP completeness proof, but here the problem is what? So in order to check the condition, so whether we can obviously non-deterministically guess a tour, and then we would have to figure out what is the length of the tour and see if it meets the budget. The problem is, so we don't know how to efficiently compare such a sum of Euclidean distances to a given number. That's unknown to be in NP. So we don't know if the Euclidean TSP is in NP for that matter. So you have a question?
What is the D is fixed in advance, or it's a part of an input here?
Oh, okay. Yeah, you can let it be part of the input if you like. I forgot to look up for which particular D you have NP hardness.
Okay, so it's some fixed constant.
Yeah, it's some number. I don't know, but probably even for D equals to 2, it's difficult. So for the same reason, even simple problems like shortest path also becomes we don't know the complexity in Euclidean space. So if you have points in Euclidean space, they define a graph, a complete graph, where we measure the distance between 2 points as just the Euclidean distance. We have then chosen S and T. We want to find the shortest path from S to T. So how to do that? Well, we could run like Dijkstra's algorithm if we liked, but that requires us to be able to compute or compare distances between 2 partial paths. That leads to figuring out what is actually the obstacle here, and I'd like to define that explicitly, and I'll call that, or this is called the square root sum problem. And I'll define it in a more general way than this here. So here in the decision version, we just have a sum of square roots we compare to a given number, but I want to define the case when we have 2 sums of square roots. We want to compare whether the one sum is bigger than the other. So here we are given integers, positive integers, a1 to an and b1 to bm. Let's say they're bigger than 1. The question here is now, if you take the square roots of all the numbers, you sum up all the square roots of ai's. Is that strictly bigger than the sum of square roots of the bj's? So we could say that if we get this for free, then we could solve the TSP problem. So we could say that one thing would be to say that Euclidean TSP would be in NP with an oracle for solving square root sum. So simply just guess a TSP tour as usual, and then construct appropriate numbers to be able to evaluate whether the sum of distances meet the budget.
So this is just pretty much the reduction rate.
Yeah, so you don't actually need oracle access. You just made a usual many-one reduction. That's right. Oh, I should write TSP also. So it's open whether this problem is in NP, of course. However, maybe that's just because we cannot really prove it to be easy. I think actually a common conjecture is that it can be solved efficiently. So be able to solve that in polynomial time. One thing which is interesting, so that is
this conjecture we just need to estimate and compare this. Yes.
right. So you need an algorithm that given these integers as input, decides whether or not this inequality holds.
So conjecture
Right, it's a popular conjecture to say that it's enough to approximate these to polynomially many bits and just sum them up. And indeed, that would be a natural algorithm to solve this problem. I want to say that by result of Blömer, then if you want to consider the same problem where you don't test for inequality here, but you test for equality, then you can actually solve it in polynomial time. And later work by Hunter et al. Actually showed that this problem is in a very low complexity class, namely D-log time uniform TC0. So very simple complexity class. So this I'll not cover, but just say that you can say if you negate this, then you get a weak inequality. So but you can actually rule out the equality case. So so it's just about the strict inequality. That's the main culprit. And as asked, so why not just approximate it? And that is indeed the natural algorithm. So let me talk a little bit about that algorithm. And that was analyzed by Tivari. And what is, or maybe the naive algorithm. So you want to approximate each square root and then sum up these approximations and then do the comparison and use that as the answer. And let's actually try to go over how would you actually approximate a square root. So let's say that we have a number a given as input. We want to approximate the square root of a. So how to do that? We can apply Newton's method of approximation. So Newton's method is based on linear approximation of a certain function that we set up a polynomial that we want to find a root, and then we use linear approximation of a guess to find the next guess and then keep improving. So we'll set up a polynomial where the square root of a is a root. So we want to define f of x to be equal to simply just x squared minus a. And then we want to find a root of this polynomial. And so Newton's method, we set up an initial guess. And here we could say that we simply guess that x should be equal to a. So that's overshooting the square root of a. And then, given a guess at step n, we compute the next guess, where we say that xn plus 1 is equal to, so then we say, we take the previous guess and, how is it? Then we evaluate the polynomial at the previous guess, and divide by the derivative of f evaluated in the previous guess as well. So you see what, if you compute this, what is it then? So it's a half times, yeah, you could compute it out. So maybe not do it because there's no space here. So it looks like this. So you take, sorry, I add here. So I take the previous guess, then I add a divided by the previous guess and take the average of these two numbers. So this gives you a series that is converging to the square root of a from above. So it's monotonely decreasing towards the square root of a. So you can also do the error analysis of that, and but I think I'll not do that. But say a nice property of Newton's method is that we have quadratic convergence, convergence. So the number of correct digits is going to double, approximately double in each step of the iteration. So we want to find out how many correct digits do we need to be able to how many correct digits do we need to compute in order to be able to correctly answer this question by the approximate version. This you can analyze directly and by somewhat elementary means, but since I'm going to use it later, I'm going to apply a big hammer of real algebraic geometry, which we'll just take as a fact. So let me write down that. So we're going to look at the case when we have a bunch of polynomials. We have S polynomials. They have integer coefficients, and they are in, let's say, k variables. And we also look at what is their degree. And we also want to look at what is the magnitude of coefficients. So I'm going to measure that by the bit size of the coefficient. So the bit size of an integer is just the amount of bits you need to use in order to write down the number in binary notation. All right? So they have degree d and bit size tau. And now I want to say what is a sign condition of such a bunch of polynomials. A sign condition is, let's look at these polynomials. Let's consider a point in Rk, and let's record what is the sign of each polynomial. Is it positive, is it 0, or is it negative? That is just a sign condition. So we're going to say that a sign condition is realizable if there's a point in which the polynomials get these particular signs. And now I want to say that any possible sign condition that is realizable is actually realizable by a certain bounded magnitude of coordinates of the point. So let me write that down. At a point Z in the ball centered around the origin and of radius r. And what is the radius? So it is going to be exponential in the bit size, so 2 to the tau, and then we take the degree to the big O of k. So instead of sign conditions, you can also think about roots. These are particular sign conditions. These are where points where all the polynomials are 0 at the same time. So then this statement here is saying that if there's a root of the system of polynomials, there's going to be one where located in this ball of radius capital R. So capital R is exponential in the bit size, exponential in the degree, and doubly exponential in the dimension. So I'm going to use that to analyze the precision needed for this algorithm here. So we wanted to compare two sums of square roots. So I want to write down a system of equations that I can apply to apply this result to. So let's consider the following thing. So we have integers a1 to an, and let's say they're at least 1. And let's also have signs s1 to sn, they're plus minus 1. So that'll just allow me to write up the difference between the sums of square roots of ai's and the sum of square roots of bj's. So I want to look at the quantity s, which is the sum of si's times the square root of ai, I from 1 to n. So I want to have a statement saying that either this number here is 0, or we have a lower bound on the magnitude of this number. Right? And I want to apply this result to get that. So I'll write down a system of equations. So I'll take variables x1 up to xn, and I'll set up equations such that xi is going to be the square root of ai. So I want to say that x1 squared minus a1 is equal to 0, etc., up to xn squared minus an equal to 0. And then I'm going to take one particular new variable, let's call it y, and let's multiply that by s, capital S. So it means that I do s1 times x1 up to sn times xn. I want to set this equal to 0. All right, so this system here has a solution. So the solution is that you set, you want to set the xi's to be the square roots of the AIs, and then this here becomes the sum that you're interested in over here, and y is going to be the inverse of that. So there's a realizable sign condition. So we have a root of the system which is exactly where xi is the square root of ai, and y is the inverse of capital S. Okay, so actually, now I'm getting a little worried. Now I wrote it, so maybe these can be, the xi's can be negative also, but then I'm gonna add in the individual variables x1 up to xn. So I'm gonna say that all these are positive. All right. So then the only solution is that they are the square roots of AIs, and y is actually the inverse of S. So we have a realizable sign condition. And this theorem here says it's realized at a point in this ball centered around the origin.
So shouldn't it be 1 here? I mean, what does it mean inverse? Real numbers.
Oh, of course. Yeah, sorry. I imagined I wrote a 1 actually. Thank you. Yeah. Otherwise, it doesn't make any sense at all. Yeah. So please interrupt if there's anything crazy. Right. So I confused myself. In my notes, I had moved this as a -1 equal to 0. So that's the thing. So we want to figure out what is this capital R. So here we have a system in n-dimensional real space, I guess n+1 dimensional, and the bit size of coefficients, well, that's the bit size of the given integers to begin with. So let's say that bit size of these numbers is at most tau. Then tau is also the bit size of coefficients of this particular system. And what else do we need? So the degree of the polynomials, and the degree of these polynomials is 2. So we're going to have a solution yeah, so let me just write out what the capital R is. So we take capital R to be 2 to the power tau, and then 2 to the big O of n. That's the magnitude of these numbers. So it in particular means that y is bounded in magnitude also by this number here. And it means that the capital S is bounded below by the inverse of that number. So we get that S is at least 2 to the minus tau 2 to the big O of n, unless it's 0. So it might be 0 or it is equal to that. So if it is 0, then I don't have a solution where I have an inverse, of course. So but that's also the statement we're looking for. So either it's 0 or it's bounded below by some bound. So if it's not 0, we have this solution where y is the inverse of S, and it's bounded below by this quantity here. So this also gives us the amount of digits that we need to approximate each square root with in order to be guaranteed that we do not make any mistakes in the algorithm. So that is the log of this number here. So we can see that the number of digits needed is this particular number. So it's enough to approximate each square root to an exponential number of digits in n. And how many iterations do we then need of the Newton iteration to do that? So that's a log of this number here. So we need just to do log of tau plus order of n iterations of the Newton iteration to be able to get sufficient precision. So that's an algorithm that runs in polynomial time for solving the square root sum problem, right? So we just do a polynomial number of steps of the Newton iteration algorithm. Each step of the iteration is polynomial time. However, the caveat is, of course, that we keep full precision of the numbers in each iteration. So this is not what you do in practice, but this is what we need to do here. We need to get exponential precision, so we need to actually write down exponentially many digits, and that is not polynomial time in the normal Turing machine model of computation. So it's not a polynomial time algorithm, but maybe we can analyze this better and only have to do polynomially many bits of approximation and get a real polynomial time algorithm. And then you wouldn't actually need to do Newton's method. But we can consider this to be a polynomial time algorithm if we allow unit cost operations on numbers. All right, so we'll study a model of computation where we have unit cost operations, and we don't care about the bit size of numbers. And I'm actually going to talk about the so-called Bloom-Schupf-Smale model of computation, and that works with arbitrary real numbers as inputs. And yeah, so let me do that. Any questions so far? All right. So Bloom-Schupf-Smale defined a model of computation that works over actually any ring. In particular, the machine, if you look over the ring of integers modulo 2, so just the bits, you recover the standard bit model of computation, so standard complexity as you're taught with Turing machines. But here we are going to just focus specifically on the real numbers. But a lot of the things I'll say would work over any ring. So this will then give rise to, once we have the machine model, it'll give rise to new complexity classes now over the real numbers. So let me introduce what the machine is all about, and I'll just try to sketch it. Please answer ask any questions if there's anything unclear. But we'll talk about what is the input space and what is the output space to begin with. So I'll use the notation of Bloom-Schumann-Smale and use this reals to the infinity, and we'll have an output space which is also a subset of that, and this here is simply just the union of all possible lengths of n-bit, dimension n vectors over the real numbers. So just arbitrary long, you can say strings, but where every letter is a real number. All right. The state space is also going to be real numbers, and just like a Turing machine, we'll have an infinite number of registers that we can work with. We can think of this as being a tape where each cell just doesn't store a symbol of an alphabet, but store an actual real number. And the notation of this is R with subscript infinity. So that's a set of all sequences infinite sequences where each coordinate is a real number. All right, so just this is modeling essentially the tape of a Turing machine. Then we're going to have a bunch of different instructions. So what can you do in each step with such a machine? And I'll follow what Bloom-Schumann-Smale have in their textbook. So we have a list of n instructions, and this is specifying the program. And these are numbered in the textbook. They're called nodes, and maybe I'll say instructions. So we'll just number them from 1 to capital N. And we have different types of operations. So we'll have an input node. So that is just node 1 without loss of generality. So that is just taking a member of the input space and mapping to the state space. So simply just taking the input and placing it in the registers. And we'll have an output node that could be we could, without loss of generality, assume that there's only one output node, and that's the last node. And these are linear maps from I into the state space and from the state space into the output space. And usually we'll in a natural way just place the input on consecutive registers. And in our case, we'll just talk about decision problems, and the output space is just going to be a single number. We want to output the characteristic function, so always output either 0 or 1. But they define everything in a very general way.
But so it can be any linear.
Yeah, I think in general it can be.
So you are saying that you usually have that you just place registers into the tape, but your tape is infinite, so what you will have in the other register?
Also, so the other registers will just be initialized to 0. Yeah. So typically you also need to somehow mark, yes, you'd say what is linear map. So you can have a separate linear map if you like for every input length, or it should somehow be uniform in some way. Yeah, so I think I'll skip the details, but just think of placing the input on consecutive registers. And you also want to mark somehow or give the machine knowledge of the length of the input actually. So maybe some of the coordinates are 0, you want to distinguish these from the blank registers or unused registers. So where the real thing is going on is computation notes. So what you can do there is that you can apply a rational function to the state space. And yeah, why not call it something? And you want that it only depends on a finite number of registers and only changes a finite number of registers. And then we're going to have branching nodes or branch nodes. So you can actually do something. And what you're allowed to do is that you can apply a polynomial to the state space and then branch depending on the sign of this polynomial. And this depends also on a finite number of registers. So usually you would just go to the next operation. If you process the input node, you would go to the next instruction. And likewise with the computation node. But here you can then branch, so you can go to an instruction or a node depending on the sign of this polynomial. So P of x is the current state, say. So for now, we are only able to treat finite objects. We need some way to access arbitrarily long inputs. And in this presentation, we'll do quite similar to a Turing machine. So we're allowed to shift the tape that corresponds to shifting a tape head. So we'll have shift nodes, and these will shift the registers one position left or right. Maybe not the actual registers, but the contents of registers. And that's that. So that's like a rough description of the machine, what it is doing. So it receives the input on, let's say, in dimension n on the first n registers, and also plays maybe on the 0th register the number n to say how long is the input. And then we go to computation nodes. We can do operations on registers, and we can do shifts to access arbitrary contents of the input, and we can branch depending on the computation so far. This allows us to express all types of algorithms that we'll be interested in. Maybe I'll make one short remark, is that in Computation Notes, so here we are allowed to have rational functions, so ratios between polynomials, changing multiple registers. So you could, this is just for convenience if you actually want to write down a concrete algorithm, but if you just want to study the model, you could, without loss of generality, assume that you just do very simple operations only involving, let's say, reading two registers, applying an operation, and writing to a third register. So we could have that operations look as follows. So we take xi and we assign that to be xj applied with some operation with xk, where the operation is going to be plus or minus and times or division. And then we need one more operation assigning a constant to a register. And in the Bloom-Schulp-Smale model of computation, you actually allow for arbitrary real constants. So that's part of the description of the algorithm. So that could be anything you like. Also, the branch nodes could be without loss of generality, just depending on the contents of the single register. So you don't need to compute a polynomial. You could compute it beforehand using computation nodes or primitive operations, write in a register, and then do the branch. Right, so any questions about the model? So just take it as a model where we have real numbers, we can operate on these and do basic operations and compute away. Then we can define complexity classes just as, if you think of in an analogous way as for Turing machines, we can define P and NP in this Bloom-Schulp-Smale model of computation. So that is P with subscript reals. So that is decision problems computed in polynomial time on a Bloom-Schulp-Smale model, on a Bloom-Schulp-Smale machine. So you can think of these as maybe not languages, but sets. In polynomial time on a Bloom-Schulp-Smale machine. Yeah. We can also define NP. So I guess there are two ways you could do it. So in the classical model of Turing machine computation, you would either define non-deterministic Turing machines where you augment the transition function by having multiple choices, so it'll be a relation, not just a function, or you would write it as a witness checking procedure. So you have languages, you need some other language that's a witness checking language, which is decidable in polynomial time. You would do a similar thing here. So you would have decision problems that has a checking language in polynomial time. So let me just write that rather informally. Language or problem. So here, given a pair of x and y, so input and witness, we want to compute whether we have an actual witness in polynomial time on a Bloom-Schulp-Smale model of computation.
So then you have a problem about this model?
Yeah, of course we have a nice open problem whether polynomial time. Excuse me?
Which one? Not just not to miss.
problem would not be very.
I think they asked for something in this model.
No.
So this here is a problem also, and you can think about whether it's related to the classical problem, of course, and there's some work on this, and I think this is beyond the scope of the talk today.
We would not receive the young guys. We would not receive 1 million for so many.
No, you would not get 1 million, unfortunately.
Bullion, okay.
Yeah, you'll get a real million. You'll not get a real million. So let me say one other thing is, so an outstanding open problem in this field is whether linear programming is contained in polynomial time. So we don't know whether we can solve linear programming with real valued input in polynomial time. So we have a polynomial time algorithm in the bit model of computation when we can look at the numbers given as rationals and then compute like interior point algorithms.
Is it related to strong?
This is very much related to the question of strong polynomial time. However, there's a caveat, of course, is that this is unit cost, so we can actually produce numbers of big magnitude, which we cannot do in the bit model of computation. So I don't think it's quite equivalent. We cannot translate a polynomial time algorithm in the Bloom-Schupf-Smale model directly to the bit model of computation for this particular reason.
The definition of strong polynomial time is very big. It is not accidentally, by the way. It was because it was the main, the opponent was very upset when the polynomial time algorithm appeared, and they said that they want something different. They wanted even strong polynomial, but it is not strongly defined.
Right, okay. All right, so that's the model of computation, and just like Turing machines, I'll not actually use it, but just know that it's there. So now I'll erase it all again. And but you do get a theory which behave in an analogous way as the classical Turing machine model of computation. So we can define, again, universal Bloom-Schupf-Smale machines and also polynomial time reductions in an analogous way as Turing machines. So let me write that. So next thing you would do in ordinary Turing machine complexity is now to prove the Cook-Lehmann theorem. So proving that satisfiability is complete for NP, and we'll prove a similar result here for the Bloom-Schupf-Smale model of computation. So we'll prove that a particular problem is complete for NP over the real numbers. So let me define the problem. So that it's a problem polynomial feasibility. So we are given a system of polynomials over the reals, and we want to figure out if the system have a root. And now the polynomials are over the reals. So we get actually real coefficients as input. And the question is just, is there a root? So is there x in Rk such that pi of x is equal to 0 for all I? And the theorem is that this is complete for NP over the reals. So clearly we have membership in NP over the reals. So if we get as input such a system of polynomials, we would simply just non-deterministically guess a root of the polynomial and then evaluate each polynomial and check for being equal to 0, and then write the output 1, otherwise write the output 0. So the real work is going on in the NP hardness. And here I don't want to do the proof in details, but leave most of it just as an exercise for you, but maybe highlight a bunch of things you want to do. So we're given a fixed Bloom-Schultz-Smale machine, and we're given an input. We want to write down a polynomial system that has a solution if and only if there's a witness making the machine accept. So we are given a Bloom-Schultz-Smale machine. And we have an input length in mind. So I guess the machine is fixed, and now we're given input x of length n. And let's assume this is the witness checking machine for the language, and this is the input. There are going to be some additional inputs which represent the witness. So we need to define some polynomials. So that means we need to define some variables, and we need to define some equations. So how should we represent the computation? So we want to represent by variables the content of each register at each time step. So let me erase some stuff over here. So variables, we could take xit to be representing the state of register I at time step t. And we also want to have variables representing what is the current instruction that is executed by the machine. And let's call them something. Maybe call these YT, why not? Something like this, and now you want to write down equations expressing that computation proceeds according to the stated program. So that'll be the exercise. So one thing that you'll probably like to have is that you want to express or convert these into indicator functions, indicating whether at a given time we are at a given instruction, we're executing a fixed instruction, having that as an indicator variable 0, 1 to be used to express the polynomials you need, and Then maybe the tricky case is a branching node. So you want to be able to extract the sign of a polynomial. So let me say how you could do these things. So let's say that for the first thing, you want to maybe make this indicator function, which is 1 exactly if the current instruction with input y, so y runs from 1 up to capital N, is actually equal to little n. So you could just make a product here where j runs from 1 to capital N, excluding the n you're interested in, and then take y minus j, and then divide by n minus j. So this here is equal to 1 if y is equal to n, and it's 0 if y is not n, and it's actually a number from 1 up to capital N. Yeah. So that's something that can be useful to building these polynomials that you like. Let's talk about the branching operation. So suppose that we have computed a value in a register x, and now we'd like to branch according to the sign of x, whether it's positive, 0, or negative. So consider some register variable x, and we want to branch according to that. So I'll define a new variable in this case. So I'll take a fresh variable, let's call it u. And now we're going to add a particular polynomial to our system. We're going to add the equation x times, I'll call the variable u, x times u squared, and let's make it minus 1, and then x times u squared plus 1 equals to 0. Let's stipulate that that is an equation that needs to hold for our variables. Let's consider the cases where what happens. So we can have that x is 0, it could be strictly positive or strictly negative. So if x is 0, then let's look at x times u squared. Then x times u squared. So this will have a solution where when x being 0, and x times u squared is, of course, equal to 0. If x is strictly positive, well, u squared is positive, so the only way to get a solution in this case is that u squared needs to be the inverse of x. So x times u squared needs to be equal to 1. And if x is negative, well, again, then u squared is positive. We need to have that now that x times u squared is equal to minus 1. So now, by introducing a new variable and adding this equation, we have now obtained an expression, namely x times u squared, to be equal to the sign of the register variable x. And then we can use this to build equations telling you that you branch to the correct instruction and so on. All right, so I think this was maybe the troublesome case. Now it's just a matter of writing down or doing the tedious work of writing down the actual equations. Yeah, so for instance, the computation notes. So you want to say that some register is now a polynomial function of, or rational function of the previous registers that naturally turns into a polynomial equation, etc., etc. All right, so that was now showing that the polynomial system feasibility is complete for NP over the reals. Now I want to show or talk about two other problems which are also complete for NP. So one is quad, and that is what we'll be using in the as a workhorse or the starting point in the lecture tomorrow. So this here is just feasibility, where all the polynomials have degree at most 2. And it's quite simple to make a reduction from feasibility to quad. So you want to build up monomials piece by piece. So a monomial is just a product of a bunch of variables, and now you want to build up this product, adding a new variable one at a time. So you'll introduce auxiliary variables for doing each monomial. Now you need to add up monomials. You add one monomial at a time by a single equation. So by adding auxiliary variables, you can do everything in degree 2. The other problem I want to mention, which is a quite standard problem, is the 4 fees problem. This here is feasibility with just one polynomial, so it's a single polynomial, and it is of degree at most 4. And we're going to make a reduction from quad to this problem, and what you do is you just take these polynomials, you square them, and then you add them up. Right, so since we work over the reals, you square these are going to be positive numbers. So the only way that they can sum up to 0 is that all the terms of this sum is 0, meaning that we have a root of the system. So that is an NP-complete problem over the reals. All right, so that sort of concludes my introduction to the Blom-Schupf-Smale model as such. And from now on, we'll switch to the bit model of computation. We'll try to relate this to the bit model of computation, but be more like the bit model of computation, namely that we take away the peculiar properties of the Blom-Schupf-Smale model of computation, that we only want to consider discrete input. So input are just given by bits, so just discrete. And we don't want to have arbitrary real numbers in our computation. So this is going to be constant-free Blom-Schupf-Smale models. Constant-free Blom-Schupf-Smale machines with discrete input. So there's some notation for this, and so there's this notation here, P over the reals with a 0 here, so that is a constant-free fragment of polynomial time over the reals. And we also have NP, the constant-free part of that. So constant free, we still have constants, so we just allow constants 0 and 1 in the given computation notes. And then the Boolean part. So the Boolean part of such a language or decision problem over the reals is simply the intersection with binary strings. So you only consider binary input from now on. And this means that we'll have this rather cumbersome notation for the classes that we're going to consider. So we are going to consider the Boolean part of the constant free fragment of polynomial time over the reals, and the Boolean part of NP over the reals without constants. And I'll say some properties about these classes. So in particular, this class here is what we'll be focusing on in the second lecture, and it has gained quite a lot of attention recently. There are some alternative names for this class in the literature at the moment, or has been used historically. There's NPR by Burgess and Cocker. There's Exist Reals by Schaefer and Stefankovich, and there's also ETR used by some papers in algorithmic game theory. It seems that most papers are considering this notation here. That is what we'll use also. This here is a normal complexity class. Discrete languages are contained in this, and you can think of just quad as being the complete problem for that class of problems. I have a bunch of other stuff I would like to say, so I'll end in 5 minutes, or so 5 more minutes, or yeah. So let's see what I want to say. Let me maybe explain this part of the title. So what is the existential theory of the reals? That is yet another problem. So studied in real algebraic complexity. Maybe let's start with the first order theory of the reals. This here is the set of true sentences. So we can have quantifiers, quantified variables, and as atoms we're going to have polynomial equations and inequalities. And the existential fragment, which I could also write ETR, so that is the existential fragment of that. So think about it as being that we existentially quantify a bunch of real variables, and then we have a quantifier-free formula here whose atoms are polynomial equations and polynomial inequalities. It was shown by Tarski that the first order theory of the reals is actually decidable, and later more efficient algorithms were developed. So we actually know by Rennegar that the first order theory of the reals is contained in X space. So that's one thing we know, and we know by Canny that the existential fragment, I should say, is contained in is in polynomial space. This also means that this complexity class here is a subset of polynomial space. So it's lying someplace between NP and polynomial space.
Pardon me, but is the text of Canny or the proof of Canny, does it exist anywhere? There was a record.
Oh, the full proof or?
The full proof. What is the proof?
Yeah. I'll.
It's like public mind, but
Yeah. So I'll admit I didn't read his paper. The result also follows from Rennegar's, who actually wrote 3 papers with full details on this. And it also follows from later work. So, but it seems that this is the reference used in the, or he's given the credit for this in the literature at least.
it was never published in journal.
Yeah.
Paper and stock and nothing more.
Right. Yeah. So you probably know better than me whether it's actually
Somebody wrote something intelligible.
right. Anyway, the statement is true. It is a subset of P space. Let's see what more can I say. I think I'll just spend maybe overshoot a couple of minutes and also relate this class here to the standard bit model of computation. So I'll use this tomorrow and rewrite it. Let me introduce another problem called post-SLP. So we are given an arithmetic circuit with constants zero and 1, so essentially just 1, and operations plus, minus, and multiplication. And it's computing some number, some integer n. The question we want to decide is this number actually positive? So we have the following proposition, and the problem was introduced by Allender et al. So this class here, the Boolean part of polynomial time over the reals without constants is equal to normal polynomial time in the Turing machine model with oracle access to the post-SLP problem. And I can give the proof with just orally, I think, without too much trouble. So one direction is quite obvious. So which one is it? So it's quite obvious that this problem here is contained in this class here. So we can simply simulate the normal Turing machine computation in the Bloom-Schupf-Smale model. And when we generate a problem to the POS-SLP problem, we'll simply evaluate the circuit. And we can do that in polynomial time and continue our way. So what about the other direction? So we have a computation in the Bloom-Schupf-Smale model of computation. We want to simulate it in polynomial time with access to this oracle. So what we'll do is to simulate the computation, but we'll actually never compute the results. So all the registered contents are being stored as arithmetic circuits. So whenever we do an operation on registers, we'll combine two circuits into a new circuit. So what about divisions? So we'll separately represent each register by two arithmetic circuits given the numerator and denominator. And then when we actually want to simulate a branch operation, then we're going to build a circuit to query the POS-SLP problem. So this gives a maybe more familiar interpretation of what is actually this class here. What Allender et al. Also showed is the following thing about POS-SLP. One minute. So Allender et al. Showed that the POS-SLP problem, so it's obviously contained in P-space, but they give an improved complexity theoretic upper bound on this problem. So it actually lies in the so-called counting hierarchy. So let me just write it down. So there's a class PP, so that's just like NP, or a probabilistic class where you just want to be correct with probability half. This would give the first or the 1.5 level of the counting hierarchy, but we want to move up to the 4th level of the counting hierarchy. But complexity theoretically speaking, this is definitely an improvement on the P-space, trivial P-space upper bound given by Kenny's or others' argument. I think an outstanding open problem is to get from a complexity theoretic viewpoint, to get an improved upper bound for existential theory of the reals than P-space. So I think this is all I'm doing today. Let me just say what I'm going to do tomorrow. So we'll start with the quad problem, and then use real algebraic geometry, the bound I had written here to get to a problem that we can use to reduce to decision problems about games. I'll look both at normal form games and some turn-based games where we consider decision problems. Right? So thank you. I hope to see you tomorrow.